So today we're going to again look at using the unit circle to help us find our different trig ratios. But first, to just review kind of how we define angles in trigonometry. It's a little different than with a triangle because they're not as static. So what we want to think about is every angle is going to have what we call an initial side, right? And then it's going to open and then have a terminal side. So initial and terminal just kind of indicate direction. So what I think is a nice visual image here is you can think of the angle as opening from the initial to the terminal. Okay, so with that we also define a direction. So this angle I just drew, we would say it's counterclockwise. Right? It doesn't go anti-clockwise or counterclockwise. So by definition, in trig, positive angles open counterclockwise. So that's just how we define it. It's helpful to think about, to help remember that, is if you think about our 4 quadrants and how we number them. Right, we start here at 1 in the first, well, that's the first quadrant, and then we go counterclockwise. It's the same direction an angle would open. Okay, so that's how we open. And that would be a positive angle that opens clockwise. If it opens, or counterclockwise, if it opens clockwise, it would have a negative on it. So all the negative tells you is that it opens in a clockwise direction. If it's positive, it opens in a counterclockwise direction. So it's kind of like 2 pieces there, direction piece. We're most interested in angles in standard position. Okay. So an angle in standard position, and this would be good to jot down if you don't know it on your paper there or in your notes, whatever, just to make sure you can refer back to it. And just the act of writing it down can be helpful sometimes. But an angle in standard position has its initial side on the positive x-axis and its vertex at the origin, right? So the vertex would be at the origin, the initial side would be on the positive x-axis. So if we drew the angle, let's say 120 degrees in standard position, so this would be 120 degrees in standard position. Our vertex would be right at the origin. The positive x-axis would be our initial side. And then we need to just think what 120 degrees would look like. So we know that if it opened to where the terminal side was straight up, that would be 90 degrees, correct? And that would be over here, would be 30 degrees more. So this would be 120 degrees. Does that look okay to everybody? Now, what's really, one thing that we really can get a handle on, and it'll make everything a lot easier, is whenever we're measuring angles, or if we talk about reference angles, or we talk about trying to put the triangles in the unit circle like we did last week for all 4 quadrants, we always want to measure our angles off the x-axis. Okay, always measure them off the x-axis. So for this one, if you didn't, hopefully you know a terminal point or whatever, maybe in the first quadrant that you can reflect over there. But if you didn't, what we can do is we would want to look at this angle right here, right? And this would be called our reference angle, which a lot of times you'll even call theta bar. You put a theta with a bar over it. And what that is this is the smallest angle formed by the x-axis and the terminal side. Now also your reference angles will always be positive. You're not really going to worry about direction on those. Okay, don't worry about the direction on those. You'll be in good shape. We don't need to worry about that. So for this one, if this was 120, we know that halfway around the circle is 180, correct? So what would that make our reference angle here?
66.
It would be 60. So theta bar in this case would be 60 degrees. That means if we need to put a triangle in there to help us find our ratio, we think back to our 30, 60, 90 right triangle, and it would, fancy here, use a purple marker. But if we do this, right, if we remember back to our special right triangles with a hypotenuse of 1, right, this would be 1, this would be radical 3 over 2, and this would be 1/2 in terms of those triangle lengths. Does that seem familiar with everybody from last week? Now, this is an x value. Do you think x is going to be positive or negative in the second quadrant? It's going to be negative, and then y would be positive. So that's how we can still use those right triangles, even though obviously you can't make a right triangle with a 120-degree angle in it. I mean, if you try it for like a minute, you'll be like, oh, that's not going to happen. Right? It's just not possible. But we can still use that right triangle as we move to other things. And this is one way you can build your unit circle and you can find those values. There's other ways too. You just kind of have to find whichever one sits best with you. Right? Just what you like best. So with this in mind, what we'd want to do in this case is out here, if we think about, now there's an infinite number of points on this ray here, correct? On this terminal side, but there's one that will hit the unit circle, right? And that ordered pair would be negative 1/2 radical 3 over 2. That's a really bad 1/2, isn't it? So negative 1/2 radical 3 over 2. So if we know that point, which we should, right, because we looked at our unit circle last week and we worked our way around it and we talked about symmetry and all that, we're going to be able to find all 6 trig ratios for 120 degrees based upon that point right there. So that's what we wanted to find today, is how we can use a terminal point on the unit circle for a given angle to find all 6 trig ratios. So let's take a look at that. Okay, so if we look at the worksheet, we're given this picture, and this is just some generic angle T, right? We went ahead and drew it in the first quadrant just because it might seem a little easier, but this would be the same for all the quadrants, right? But again, T, you would use your reference angle if you needed to, unless you knew the big point, which we'll learn soon. But with this one, this is a right angle. As we look at this, we have our angle T, then we see that it intersects with the unit circle at the point xy. We know the hypotenuse here would be 1, right, which is nice. So what we can do is we can use this picture here, especially this one in the first quadrant. And what we know yesterday, or last class period, we talked about right triangle and how to define the trig functions in terms of adjacent, opposite, hypotenuse. We can use this to define our trig functions based upon the unit circle. And what I mean by that is, to start with, if we think about the sine of t, right? So we have this triangle here. T's the angle we want, and we know that sine is opposite over hypotenuse, correct? Well, in this case, opposite is y, hypotenuse is 1. What's y divided by 1? It's just y, right? So the sine of t is just the y value of that coordinate. So all the time we're going to get that the sine of theta is 1/2, or radical 2 over 2, or radical 3 over 2. Those are the points that we looked at yesterday. And all the other points are there too, but these are the ones that we're focused on. Now it does ask us about the domain. For this function, if you think about it, if you sweep out the entire unit circle, right, is there an x value everywhere? Sure. I mean, it's got to be, right? I mean, out here, it's the x value is 1. Up here, the x value is 0. Here, it's negative 1. I guess I could have finished the units, but they're all defined. So for this one, the domain would be all reals. You can take the sine of anything, not a problem. The next one we're looking at here is the cosine of t. So by the same reasoning, if we look at our triangle inscribed in the unit circle there, right, our standard position angle, well, we see that if you wanted to do the cosine, you would do adjacent, which is x, divided by the hypotenuse, which is 1, and x divided by 1 is just x. Now, do you think x is defined completely around the unit circle? Sure, everything has an x value. Did I say the x values for sine before? I may have. Sorry. This is where y is 1. This is where, I'm sorry, y is 0, y is 1. We get the idea there. But these are defined on those. So for this one, the domain would be all reals. If you wanted to say negative infinity to positive infinity, you could. However you want to define that, it's all real numbers. So those are the big two. To realize that every point on the unit circle, that the x-coordinate is the cosine, and the y-coordinate is the sine. Okay, that's huge. And really, if you know that, we can build all the other ones from that. Because we have one more rule here that we didn't talk a ton about, but is very readily apparent now that we look at it, and that is, if we do the tangent of t, we know the rule for tangent, the ratio is opposite divided by adjacent, right? So that would be y over x. But we also know that y is the same as sine, and that x is the same as cosine. So this is also equal to the sine of t divided by the cosine of t. This is a super valuable identity, right? Because then if you know the sine and cosine, you can produce the tangent without much trouble. Okay, now on this one, if we look at the domain, here we have x in the denominator, so we still can't divide by 0, right? That's still a thing that we can't do. So if you think about your unit circle, when would x be 0? Well, it would be 0. Finish this unit circle up a little bit. But it would be 0. Close. Not my best work. But x is 0 right up here, isn't it? And it's 0 right down here. So what would you call this angle? 90. What about this one? So let's see, this would be 90. So this would be 180, wouldn't it? This would be 270, right? This is 360. Now, can we keep going? We could go forever, right? We could go negative 90, negative 180, negative 270. So we need kind of a fancy way to write this. What you notice, though, is it's always whatever's up at 90 or what's called a coterminal angle. Somewhere else that has the same terminal point is 90, right? Whether it be 360 or 450, right? You go up here. So what we're going to say here is for the domain, we're going to say x, not x, we're going to say t, which is the central angle. T cannot equal 90 degrees plus 180 degrees times n. Because what we're doing is n is just going to be some integer, right? N is just a counting number. 1, 2, 3, negative 1, negative 2, negative 3, all that stuff. So with this, we're going to say n is contained. This is some really lazy shorthand here, but it's pretty cool. This symbol here, this z with these double lines, is called the set of integers. So this just means that n is any integer. That's just that's shorthand there. This is like a C crossed with an E that we've used that some. And that's just a Z with like a double diagonal, called a whatever. But what that means is, so it doesn't work at 90 degrees, right, when n is 0. And then if n is 1, it tells you it doesn't work at 270, right? And if n is 3, it tells you it doesn't work at 450, right? And you keep going around. If you think about negatives, if you put negative 1 in, that means that there's no tangent at negative 90. If you put negative 2 in, there's not one at negative 270. So it's just a way to say that if you're straight up or straight down, the tangent's undefined. Is that okay? I know the domain notation's a little strange. The next one we want to do here is, I guess we're doing cosecant of t. And again, I don't ever really think of what cosecant is. I just think it's the reciprocal of sine. So the easiest way to think of this is just say, well, that's 1 divided by the sine of t, isn't it? And we know the sine of t is equal to y. So that's just 1 over y. That's how we're going to get that one. All right, and then from there, once we've done that, now we can't let y equal 0 for our domain, right? That would be a problem. You can't divide by 0. Well, we see that y is 0 at 0 degrees, right? At 180 degrees, at 360 degrees, it's 360 plus 180, whatever that is, 540, right? 720. So I feel like I'm in a skateboarding competition here because those are the numbers they use, right? It's either a rotation or a rotation and a half or 2 rotations. So what we'll say here is that t cannot equal 90 degrees, 180 times n, right? Because if n is 0, that gives you 0 degrees, right? If n is 1, it gives you 180. If n is 2, it gives you 360. Right? If n is -1, it gives you -180. All that stuff. Does that seem okay? So basically, out here and out here, that's undefined. Again, n is contained in the set of integers. Right? So bear with me here. We just got the last two, and then we're going to be in pretty good shape here. So the last couple, we have secant of t. How did we define secant? We had some rule for it, but we said it's the reciprocal of what? Cosine, right? So that's going to be 1 over the cosine of t, which is just 1 over x, right? The cosine of t is just x. We define that right here, at the top of the page there. Now, again, do you think it's going to be a problem if x is 0? Sure. It's going to be the same domain that we had over here for tangent. And again, you can't let x be 0, so you can't be up at 90 or down at 180. Is that following for everybody? And again, this might be helpful too. If you have your unit circle out, you can notice that straight up and straight down that the x values are going to be 0, and that would be a problem. So here for our domain, we would say t cannot equal 90 degrees plus 180 degrees times n, where n is contained in the set of integers. If you use a little variable in your domain, it's proper to define what that variable is each time you use it. So that's why we have that nice shorthand there. Last but not least is the cotangent. Now we looked at how tangent, we could write it as sine over cosine. We could do that same thing with cotangent also. We also, though, we have some options here. We could write this as 1 over the tangent of t, right, which is something we talked about. That's the reciprocal of tangent. And since tangent was y over x, that means the cotangent would be x over y. But then also you can define it as the cosine of t over the sine of t. So they're all correct all the time. You can always use whichever one you want to use. Right? It's fine. This one's not great though, because if tangent's 0, you get 1 divided by 0, which is probably not loving that. Right? You might want to switch it for a different one. So with this one again, our problem is going to be where y is equal to 0 would be our domain issue. So we're going to say the domain, just like we did with cosecant, is that t, whoops, that should be not equal, cannot equal 180 degrees times n, where n is contained in the set of integers. Okay, so this is how we define the 6 trig functions on the unit circle. Again, we made the connection with the triangle here, right? But pretty much the way we kind of explained it is I just used that to describe the sine and the cosine, maybe the tangent, then we just used our reciprocal rules to find the other ones. Like if you learn sine, cosine, and tangent really well, it's always a case of just flipping them later on, which I think cuts your workload in half, rather than trying to learn 6 independent quantities. You learn 3 of them really well, and then it makes it nice to go from there. Okay, so for an example here from the back of the worksheet here, we're asked to find the 6 trigonometric functions of each given the real number t. So t is 90 degrees, right? And we're going to look at different ways of expressing this real number soon, called radians, which makes, I think, even more sense sometimes. But our first order of business here, is we want to draw a 90-degree angle in standard position, meaning the vertex is at the origin, the initial side is the positive x-axis. We all know 90 degrees is straight up, right? So let's go ahead and do that. Now, hopefully, because we realize we're inside the unit circle and all of the, I can show that it opens right to 90 degrees, use a little arrow there on my arc. But we should know this terminal point right here, correct? Again, you could use a lot of different terminal points, but we want to use the one with the hypotenuse of 1. It lets us use those ratios. Anything that we did, if the hypotenuse is not 1, then sine is no longer just y. It would have to be y over your hypotenuse length. It's more work. So what would this terminal point be up here?
0, 1.
That would be 0, 1. So now, as we kind of want to do our 6 trig functions, we have some options, but I think definitely you want to start with the sine of t and the cosine of t, because those are actually just the values we have right there. We know the x-coordinate. What did we say it was?
0.
Well, it's 0, but is that the sine or the cosine? It's cosine. I always remember it's like x comes before y and cosine comes before sine, and like in the alphabetically. I don't know how I always think of it. So we get the sine as 1 and we get the cosine as 0. A lot of times you'll even see a terminal point written as cosine t, comma, sine t. Right? That's the activity we stopped halfway through last week, was what it was trying to show you, was that. So now, at this point, I'm going to go ahead and find the tangent of t. Well, that's just going to be, I could do y over x, if I remember that. I could, do lots of different ways, but I'm going to think of it as it's the sine of t over the cosine of t. Right? That was one of our definitions. The tangent is just sine over cosine. I always figured that's why you always see sine written first. I don't know that for a fact, but it always made sense to me. So sine over cosine is 1 over 0, which is undefined. And I like to put UDF. It's a local flavor. Delicious malts and shakes, and undefined. Multi-purpose. So however you want to put that, it's undefined. Not 0, it's not leave it blank and hope for the best, but you need to write undefined, or you could go with UDF. All right, so next up is I'm going to do the cosecant of t. So really, I'm thinking back to what we did last week with unit circles. I know that the reciprocal of sine is the cosecant, correct? So this is 1. What's the reciprocal of 1? Well, if you don't know that, write this as a fraction. It would be 1 over 1, wouldn't it? And you flip it, it would be 1 over 1, which would be 1. So they're both 1. And then secant of t, that's the reciprocal of cosine. So now cosine is 0. If I'm going to make it a fraction, it's going to be 0 over 1. If I flip it, it's going to be 1 over 0, which undefined. If you remember, these two had the same domain, so it would make sense that they both would be undefined at the same location. And lastly, we have the cotangent of t. Now at this point, since we wrote this, we know 1 divided by 0 is undefined, but can we still do its reciprocal? Sure, it would become 0 over 1, which is 0. So I always like to think that if the tangent's undefined, the cotangent won't be. It will be 0. That's kind of how those work with each other. We doing okay there with this? So just to finish up here, let's look at, we have this next one is t is equal to negative 60 degrees. Let's go ahead and try that, and we'll take a look here. Okay, so for this next example, we have the t is equal to negative 60 degrees, so it's still going to, we're going to always draw them in standard position. I hate to say always, but I think we are always going to draw them in standard position. And we know that if it's negative, it's going to open clockwise, right? So what we'll get here is it'll be down here somewhere. Probably the biggest thing is make sure you hit the correct quadrant. Other than that, it's just sort of a placeholder here. now also, does it make sense that this would also, if you did like a 300-degree angle, you would have the same terminal side, correct? Those two, so in our kind of words we use, -60 and then 300 are called co-terminal because they have the same terminal side, but they have different paths to get there, right? It's like when you get done doing a 360, you're facing the same way as if you did a 0 or a 720, right? They're co-terminal angles, but obviously it's different, right? I'm not going to the Olympic skateboarding competition with a 0. You know, I think the judges would award it a 0 probably. So what we have here though is I always think this angle here is -60, or the reference angle would just be 60 degrees, correct? But that means it's closer to the y-axis than it is the x-axis, correct? So if we think, I like to think back to this point up here, which was 1/2 comma radical 3/2 in the first quadrant. So I would recommend to learn those values in the first quadrant that we talked about last week. But then down here, it would still be 1/2, but it would be negative radical 3/2. So same point, same numbers, different signs. So in terms of this, what would our sign be? Our sign function for this terminal point? Yeah, it would be negative radical 3/2. Exactly right. And the cosine? Would be positive 1/2. And then the tangent? Oh, we gotta do math. Sorry. I'm just gonna do the sine over the cosine. Okay, so that's not too bad here. It's negative radical 3/2 divided by 1/2. Does this look like a good time to multiply by the reciprocal, or the old copy change flip? Or if you realize both denominators are the same, they're going to cancel. It's kind of a thing too. But we can get negative radical 3/2 times 2/1. The 2's cancel. We get negative radical 3. For the cosecant here, we get, so I'm just going to take the sign and I'm going to flip it, correct? So that'd be -2 radical 3. Going to multiply by radical 3 on top and bottom. And that'll give us -2 radical 3/3. And what's the reciprocal of 1/2? 2. And then here we got, I don't want to flip that. That seems like a bad idea, right? But could I just put this over 1, under 1? Would be okay? So -1 radical 3. Then we rationalize it. And we get negative radical 3/3. That's what we have there. All right, so let's go ahead and stop for today. We'll finish up the last part of this tomorrow. We'll get some more practice. There is